Hey guys, welcome to the screencast for AP Physics 1 Power. This is going to be our last lesson in the energy, work, and power unit. Next up will be momentum. I've posted a boson video, I think it's work and power. You can watch that on your own. It's not really a huge requirement here, so let me just get into the notes. This shouldn't take a whole lot of time, hopefully. Okay, if you're doing any of the homework, which again is totally optional, this is going to be 34 through 41. As I mentioned before, there's going to be problems after this that are having to do with machines and efficiency. We are not going to do that, so we're going to stop at power. Okay, so we have these two groovy buses here. One is 80 horsepower, one's 100 horsepower. No, they're not too powerful, but what can the bus with more horsepower do that the other bus cannot? If you have a car that has more horsepower, what do you think that's going to mean? Well, it's going to mean it's going to have a greater acceleration. It's going to have a faster 0 to 60 time. In other words, as stated here, this one is slightly less pathetic than the 80 horsepower engine in this bus right over here. So in other words, its engine can work more rapidly. So that's a key with power, is that it's always a rate. There's always a time rate having to do with power. That's a good thing to remember. Like, for referring to electricity as power, that's actually kind of a misnomer, because power always is a time rate, as I said here. So power is just the rate at which work is done, or the rate of energy is transferred or transformed. Remember, that is going back to the work energy theorem, which is that your work is equal to your change in kinetic energy. So we can see that in the power formula, and that we can totally equate work and energy in this case. Power is defined in terms of the watt, and that is named after James Watt, another famous scientist. He actually perfected the steam engine, and so that was a huge development back in the 1800s, I believe. So we honored him by giving him the power unit. So a watt is just a 1 joule per second, and that makes sense because if you remember, P equals E over T. Well, E, energy, is in joules, and T is in seconds. So a joule per second is 1 watt. And you can also see some of the other conversions there. You can see this most commonly, like if you look at a light bulb. Now, this is a picture of kind of an old school classic light bulb. You notice it has that 60 W there. That means that this is a 60 watt light bulb. What that means is that that bulb has the capacity to convert energy 60 joules per second, and that electric energy is being converted to heat and light energy. But of course, we don't really use these types of light bulbs anymore. You're more likely to see now LEDs or compact fluorescent CFLs. You see the diagrams over here. Now I put this handy dandy chart up here to show you. You'll notice that even when we're buying CFLs or LEDs, it'll have an equivalency there, because this was the standard that we used for about a century. So it's kind of ingrained in our psyche to where, okay, if I know what a 75 watt bulb is going to light up, and generally a 40 watt bulb, I know about how much it's going to light up. If I say that I'm getting a 6 watt LED, I may not have that kind of frame of reference there. So that's where you're always going to see that equivalency there, because especially those of us in the older generation, we're not going to really be able to equate that, just because we're so used to this. Because I mean, really, up until about 5 or 10 years ago, this is what we had for like 100+ years. But think about what is the reason that these LEDs and CFLs use so much less wattage. Well, it's just a matter of efficiency. If you go back to these old school standard bulbs, if you touch one, well, you've made a mistake because they're very hot while they're on. You could just kind of put your hand there and it gives off a lot of heat. That's actually indicative of a very inefficient means of lighting because it's actually contributing much more heat than it is light. Well, if you put your hand up to an LED bulb that is running, you'll notice there's much less heat coming out. So that means it requires a lot less power to give an equivalent light, which is actually measured in lumens as stated here. And there's that kind of said there. These are kind of some older pictures. There you can, if you look at various electronic devices, you're probably going to see a wattage for that. So that just means what is the power rating? How many joules is this thing going to be able to convert from electric energy to whatever energy it needs to in terms of seconds? Now, horsepower. You may have heard this. That this is actually horsepower is actually a unit of power. It's a little outdated. It's again kind of like how we continue to use inches and feet and yards in America. But this is also a value that was originally developed by James Watt. And he used this to compare steam engines to horses because if you think back in the day, they didn't have cars. They didn't have even trains yet. At this time, it's like, okay, what is something that does power or does work? Oh, it's a horse. I mean, you pretty much had horsepower running everything then. So through testing, they determined that typically a horse could do work at a steady rate of about, as mentioned, 33,000 pound-foot per minute. And so they kind of, okay, well, we're going to say this is 1 horsepower. 1 horsepower is roughly equivalent to about 746 watts. Not exactly, a lot of times these things are a little bit off because they weren't meant to go together, but that's pretty close. Now, horsepower, you're usually going to hear that in terms of like an automobile engine, kind of like we saw at the beginning of these slides. Any kind of mechanical output, machine, engine, motor, whatever, that's about the only time you're going to see horsepower. But imagine if you're going to a car to get a car and say, okay, well, what's the power of this car? If you say it's a 250 horsepower car, you kind of have an idea that, okay, that's mid-range. If it's like 150, well, that's probably one of these little Econo box things. If it's a 400 horsepower, then you got a powerful car. If you convert that to watts, you would be a little bit lost, kind of like we did with the light bulbs earlier. Now, this is one that I really honestly miss the most with us not being meeting in person. This is such a fun activity that I look forward to every semester, and I really hate that I can't do this with you guys. But this is the most powerful person. The setup you have here is from the original slides. Everything after this I have had to totally redo for this particular semester, spring 2020, because of COVID-19 and us not being able to meet. But this is a diagram of the stairway in the Commons of Farragut High School. You have about 2.15 meters to the landing there that's in the center, and then up to the top, the second floor, kind of in front of the library where you're looking there. And horizontally, we have about 4.5 meters right there. However, we obviously can't do that, so we have the most powerful person quarantine edition. So yeah, usually I have my classes run up the stairs, we have people doing timing, and we do it that way. But we're going to have to adjust that lesson for this. So I have an alternative way, and we're going to kind of spell it out here. If you have a staircase, which would be the best way, or if there's a hill where you can reliably measure like how high it is from one spot to another, you can do this activity. If you don't have that, I'm going to provide some measurements here, and you could do the calculations and see if you get the same thing I get, because I'm actually going to provide for you my numbers a little bit later on. This is a stairway right here that is actually leading up to my apartment. I live on the 3rd floor, so I go up 2 flights of these. This is the one on the bottom. And this is a diagram. I did a little measuring earlier today, and I found that each stair is about 12.5 inches or 31.75 centimeters long or wide, however you want to look at it. And then they're about 7 inches high, or about 17.8 centimeters. We are going to need to convert this to metric to kind of play nice with our formulas. What that leads to here is that we have an overall rise of 2.67 meters and an overall run here of about 4.45 meters for that staircase. Like I said, if you don't have it at home, you can use those numbers for calculating. And like I said, I've already posted on Canvas what my results were, so you can use those, and I'm going to encourage you later on to post your own results. So if you are going to determine your own power in climbing these stairs, well, we need to remember what the power formula is. It's energy or work over time. So we're going to need to calculate energy or work and time. Well, the time part's pretty simple. That's the time it takes for you to climb those stairs or that incline or whatever. The energy is a little more complicated, so we're going to look at that in two possibilities. We could either determine the change in kinetic energy, which would be our work, or we could look at this in terms of potential energy, because remember from our past lessons, those can be kind of played off of each other to find what we're looking for. Now, if we're going to use kinetic energy, we need to know mass and velocity. Mass we can do. I'm going to show you some conversions to go directly from pounds to newtons to mass. There's a conversion rate for that. What about velocity? How do we do velocity? Well, you might be thinking, okay, well, maybe you were given the dimensions to do so. Just do a Pythagorean theorem to find displacement divided by time, but that just gives us an average velocity. We need a change in kinetic energy, and that's not going to really help us there. So we need to look at this in terms of potential energy. So remember, potential energy is mgh. If we find our mass, we know g right here is 9.8, and we know our height based on, okay, measure one stair. So if one stair is this, count how many stairs you have, and then figure out your height. And so that's the direction we're going to go with this, is solving for potential energy, because what that potential energy does is it tells us the amount of work that it took to get up to that top. Because to get potential energy, you have to work against gravity, right? And you're climbing those stairs, you're putting in work. That is the potential energy. You can imagine if you were to jump off those stairs, so to speak, that potential energy would then convert into kinetic energy until you hit the ground. But wait a minute. We had horizontal distance, and I mean, you're going upstairs, you're not just going up, you're going to the side. Why does that not work? Well, we got to look at this in terms of, remember, work is equal to FD cosine theta. Well, if we are going up the stairs, remember it's mgh. We're only doing work, if we're going up the stairs, we're only doing work against gravity there. That's the thing that we're doing work against. When you walk horizontally, I mean, yeah, you get worn out, but technically you're not doing work against gravity. And that's the only thing we're looking at here, which is why when we do the PE equals mgh, it is valid in this case. So that's how you're going to approach this. Your E is going to be mgh, and then your time is going to be the time it takes for you to go up these stairs. So what you need to do then is just take all the measurements you need, have someone time you, or you could kind of do it yourself. I did it. I live by myself, so I did it myself earlier. It did fine. And then to calculate your mass, take your weight in pounds. You can either measure it or just kind of estimate what you think it is, and multiply that by 4.4482. If you want to find your mass, then that's going to be your weight. Find your mass, just divided by g, 9.8. But, since you're in mgh, that's the same as weight times height, so you can just leave that part off. So once you've calculated potential energy, divide by time, and then that's going to be your power in watts. The final step is you're going to convert watts into horsepower, because we want to know this in horsepower, because it's a nice kind of neat number, as you'll see. So once you find that in watts, just use that conversion rate to do that. And then if you're able to do this, I want you to go to Canvas, and I've created a discussion there to post results, because it's always fun comparing, like, oh yeah, I got more than you, and I want to be able to still do that. That's really fun. So post your results. I'm looking forward to it. I did mine in 4.66 seconds, and my horsepower ended up being about 0.61. So it's not bad for an old guy, but let's see if you can do better than me. So I'm looking forward to your results, and please let me know if you have any questions. See you guys later.